Thank you for the kind introduction. Hello, Berlin. It's my first time here, and I think this is a great conference. Thank you for spending your morning at this talk. Today I'm going to talk about applications, microservices in this emerging world of stream processing. As you can tell, just from the schedule of Berlin Buzzwords, stream processing, stream data is everywhere. More than half the talks are about this subject. And there is a lot happening in this world related to this topic. In fact, unbounded, unordered, large-scale data sets are increasingly common in day-to-day business, whether it's web logs, mobile usage statistics, data from sensor networks, or the Internet of Things. Stream data is everywhere. And there is a huge push towards getting faster results. So the question is, how do you move to this stream-oriented architecture? For some time, stream processing was thought of as, or maybe is still thought of as, a faster MapReduce layer, maybe appropriate for niche problems like faster machine learning or analytics. But in my 5 years of working on Kafka and on stream processing, I've learned that stream processing is, in fact, software that computes core functions in the business, implements the business logic, and is much more than computing analytics about your business. And that insight has a lot of impact on how we develop applications and will completely change how we will develop stateful, loosely coupled microservices in the days to come. That is what I want to focus on in today's talk and tell you where Kafka and Kafka Streams fits in this big picture. So let's start off with, what is stream processing? We've used a couple of definitions for this term. So let me, use my own definition, which is that it is a paradigm for processing unbounded data sets. So if you focus on paradigms for programming, there are many ways of splitting this pie. But today I'm going to focus on a specific way, which is the way an application gets its input and the way it produces its output. And if you focus on this input-output dimension, then there are essentially 3 paradigms for programming. The first one is request-response systems. These are services that we are most familiar with. They are synchronous, they're tightly coupled, they're latency sensitive. You send one input in, and you wait for an output. And the only way to scale these services is by deploying more instances of the service. Then on the other end of the spectrum, you have batch systems. Here, you send all your input in, and you wait for systems to crunch all that data before, a couple of hours later, they send you all the output back. Essentially, the big difference is that batch systems view data as being bounded in nature. The difference from request-response is that they're loosely coupled. The latency expectation is very different. Now we arrive at stream processing. Here, you send some inputs in, and you get some outputs back. And the definition of sum is left to the program. You can have it be either one input or all your inputs. The output is available at variable times too. Either you have one output item for every input item, or one output item for every n input item. Stream processing is conflated as a notion that is related to the concept of real time. But really, it is a generalization of the 2 extremes, request response and batch. The other thing about stream processing is that it is misunderstood as being something that is probably like transient or approximate or lossy. Now, some systems might have been that way, but that is a drawback of the way some systems are designed. It isn't really an inherent property of the stream processing paradigm. In fact, stream processing systems can be made to compute accurate results, much like batch systems do, as well as do that efficiently. And there is this misunderstanding, because while processing unbounded data sets, there are various tricky trade-offs involved. And those trade-offs are correctness, latency, and cost. And some systems specifically choose to optimize or design along some of these dimensions while giving other dimensions up. when what we really should be doing is giving the user the flexibility to pick the trade-offs that are right for their application. And this is really important because one size does not fit all. Some applications really care about correctness, like billing, while some may not, like log processing. Some might care about latency, like alerting, while some may not, like ETL. While some applications actually may not be OK with fully optimizing, the cost associated with fully optimizing along the other two dimensions. So in this talk, I want to focus on stream processing and its impact on mainstream application development, how the entire company's business logic can be architected as loosely coupled, stateful stream processors. And in this talk, I'm going to walk you through this example from a brick-and-mortar retailer. For retailers, there are many inputs that are interesting, but there are really two inputs that are really important, and that is sales of things and shipments of things. And for a healthy retailer, hopefully these two inputs are never ending. So you can really represent these as streams of sales and shipments. Now, it's worth noting that these two inputs are useful for a large variety of applications downstream. So you need to send it to Hadoop or the warehouse for analytics. You send it to some kind of monitoring system for fraud alerting, or you index it in a search system. In addition to that, you might want to do some sort of incremental processing. Now, this may not be working this way in brick-and-mortar retailers today, which is that the ability to make price adjustments and inventory adjustments as demand and sales for items keep changing over time. So taking a look at this picture a little differently, at the top are things that fall in the what happened category. These are essentially events that are interesting to this retail business. And everything else is a response to that event. As a response, you might send it to Hadoop, or you might index it in a search system, or as a response, you might choose to process it and trigger inventory adjustments. And this insight actually influences some choices for the application architecture for this example. If you focus on the way applications get their input and output, like we talked about, there are a couple of choices. The first one is you don't have to worry about that at all. If you architect this as one large monolith, then the set of problems we will talk about are very different. But practically, companies don't write applications this way. Parts of your business logic are written by different teams. They're managed differently. And because they are written as separate services, they in fact need to communicate and exchange data. And oftentimes, the most common mechanism is of using synchronous communication, request-response. This actually works, but there are downsides worth talking about. First one is the total amount of parallelism, if you think about it, of processing an event through all these downstream services is fairly limited. With synchronous communication, the same sales event has to get processed one by every service, which means the total latency of processing an event is the addition of all the time taken by downstream services instead of the time taken by just the slowest service. The second downside is lack of resiliency. Things are tightly coupled. A slight degradation or failure of a service actually affects a whole bunch of downstream services. I will argue that we need to make a fundamental shift towards thinking about asynchronous communication. And this is at the heart of the REACTIVE manifesto, for those of you who are following it, is this concept of an asynchronous boundary between applications. The goal is, with this asynchronous boundary, you in fact decouple the various components of your architecture. And if you do that, then you get a whole bunch of advantages that you did not have prior to this, which is with decoupling, first of all the downstream services can process events in parallel. Things are resilient. Failure of one service is decoupled from failure of affecting other services. Now, in addition, in order to achieve this asynchronous communication, you would likely buffer this data. And for buffering, in order and processing in order, you might use a queue. If you did that, then now you have some choices. If you pick a traditional queue, then you'd have to send an event to every downstream queue one by one. If the same sales event is processed by several applications, you might want to send that event one by one to all those applications. That is wasteful. It might work. It's wasteful. As one service fails, it might fall out of sync with other services. So a natural choice is to use a pub subsystem. The need is you write it once and you read it multiple times. This greatly simplifies your architecture because now you just have one pub sub queue versus several ones. This is essentially what Kafka does. Kafka is a pub subsystem. It is a very high performance pub subsystem that allows you to write at high throughput in low latency. Okay, so the second component of this reactive manifesto is being able to handle back pressure. If you buffer events, then you have to worry about what happens when a service fails. How long do you have to buffer data in order to not run out of memory? Here I'd like to say that if your queue is in fact persistent, then you don't have to worry about back pressure. It is solved by definition. This is what Kafka does. It is a high-performance, persistent queue. It can buffer way more data that can ever live in an application's memory. So in this talk, I want to walk you through how to build a reactive retail business. An architecture that relies on asynchronous communication. It ends up with applications that are loosely coupled. They're stateful, they're resilient, and easier to develop, and also degrade gracefully. Now, part of the reactive manifesto is reactive streams. In case any of you are following that, it is a standard for streaming libraries that that dictates that a streaming library is one that processes unbounded streams of events. It asynchronously passes messages around in sequence, and it definitely has the ability to tackle back pressure. So in the remainder of the talk, you will see how Kafka and Kafka Streams actually does conform to this reactive streams manifesto, however, has a possibly different set of APIs. Okay, so back to stream processing. It is a set of functions written on top of what happened data, which we've seen that are just events. Over time, what I've noticed is Kafka is sort of rising as the de facto standard for storing stream data. And so stream processing boils down to writing functions on top of Kafka events to produce more Kafka events. Now, over time, as in the last 5 years, as Kafka has been adopted across thousands of companies worldwide, I've noticed that there are two broad approaches that have emerged as stream processing approaches on Kafka. The first one is, what I'd call do-it-yourself stream processing. This is, you take the Kafka libraries and you decide to do the rest of the stream processing yourself. And if you did that, then there are, a couple of hard problems that you should know that you'd have to deal with. Basically, even if you don't use Kafka, you have to deal with a lot of these problems to be able to do stream processing correctly and efficiently. And those are problems like ensuring that data arrives in order as well as gets processed in order. Ensuring that you have the ability to scale both data and processing out. Ensuring that you have semantics even as machines fail. Ensuring that you have the ability to manage state to be able to support stream processing operations like windowed aggregates and joins. Having the ability to reprocess data, so when you upgrade your applications, you can make sure that all your data conforms to the new logic of your application. And last but not the least, the notion of time is very important to correctness in stream processing. Now, before we talk about how Kafka and Kafka Streams solves these problems very differently, let's first take a look at the second approach, which is quite popular, which is using one of the many stream processing frameworks that have emerged since Kafka has been adopted widely. Spark has a streaming module. There is Storm. There's Samza, which some of us built at LinkedIn. There is Flink, which is a really cool technology upcoming, built locally here. Now, these systems are pretty cool. There's a ton of innovation happening in this space. If you notice that that one of the core design traits of these systems is that they're coming from the world of making a faster MapReduce layer. And as a result of that, there are some design traits that these systems share. At the core concept is taking part of your application which does stream processing and modeling that as a job that runs on these, a cluster of machines that runs this stream processing framework. And because of that, there are several implications. There is a specific way to configure your job, a specific way to package and deploy your job on a central cluster. And these systems need to think about resource management. How do you multiplex several jobs on a shared cluster? Now, these systems are actually useful for a large class of stream processing problems. Basically, any kind of iterative processing where, like machine learning or graph processing, or any kind of long-running, analytics queries that require a SQL interface actually run really well on these systems. The problems that these systems aim to solve, they actually influence the design, the system design that these systems have adopted. And I think that the only way to know if a system design is applicable to the real world is to build a system that conforms to that design, to deploy it for real applications, and then observe the adoption. In my time at LinkedIn, I was lucky enough to be part of a team that built Apache Samza, which is essentially one of these systems. And we built it, and we deployed it for in-house applications, and we also open sourced it. And through that, we learned a lot of things. The core sort of lesson learned was that one of the key misconceptions in stream processing is that it will be used only as a sort of a fast MapReduce layer. When in fact it turned out that stream processing and the most compelling applications that want to do any kind of stream processing actually look different from what a Hive query or a Spark job looks like, and in fact look a lot like what an asynchronous microservice might look like, which is different from just a fast version of your batch job. So then we arrived at, well, what needs to be done to make stream processing more applicable or approachable to application developers, since application developers develop these asynchronous microservices. And there, some of these design traits have interesting implications. If you observe, just for config management and packaging alone, there are tons and tons of tools. There's Docker and Chef and Puppet and Salt and a whole list of custom tools. For resource management, you have Mesos and Kubernetes, and that whole ecosystem is changing. Essentially, application developers are not standardizing on any one of these problems anytime soon. So we can't really dictate how applications want to solve these problems. The second is for stream processing to be approachable to applications, it has to be lightweight. It has to be something that can be embedded by just about any application. And so we arrived at this architectural decision of making this as a library. In fact, it is architected as a Kafka library, and that is done very much on purpose. Kafka already provides several primitives that are core and fundamental to stream processing. The idea is, in order to make this a lightweight layer, we have to rebuild, we have to build on top of Kafka primitives, not re-architect and rebuild what Kafka already solves. So just to give you an idea, some of you might have attended the Kafka Streams library talk, so this might seem familiar, but for those of you who didn't, Streams is a Java library. It has two interfaces. It's pretty simple. One is a callback API, and the other is a DSL. This callback API looks, pretty simple. You have a key and a value, which is essentially a message in Kafka. You implement the process API, which is your logic. As part of the process API, you might send the event out, and that's basically it. So in some sense, this encapsulates the entire scope of stream processing. You have input events, you write your processing logic, you have output events. Here's the code that you actually write to create some of these processors. The config tells it where to connect to Kafka. You have your source, which tells it which topics to ingest. You have your processor class, and then you have a sync node to tell it where to send that data. And that's basically it. This is, in fact, all that you write for your application. You can deploy it as one process, or you can deploy it as multiple processes, or you can put it in a Docker image or run it on Mesos. Kafka Streams is just a library. It doesn't dictate anything about how you should package and deploy your application. Okay, so the second API is actually a high-level DSL. It provides a sort of a functional APIs like filter and map and join and reduce and so on. Whether you use the low-level API or the DSL, or even any other stream processing system, oftentimes your operators form a topology where the first and the last nodes are possibly the source and the sink nodes, and then the remaining are operators that depend on each other. So many times the question is like, how do you map this logical topology to physical processes? In Kafka Streams, it's very simple. You just write your code and you deploy it. It does the scale out and partitioning transparently, as you will see. Okay, so now I'm going to go through some of these problems and how Kafka, as well as Kafka Streams, offers a solution to some of these problems. The first one is ordering. If you're familiar with Kafka, this might seem like a familiar abstraction. This is a fundamental abstraction at the heart of Kafka, which is a log. A log is nothing but an abstract data structure that has some properties. It is like a structured array of messages, so data is ordered. It is append-only and hence immutable, so data written once does not change. And records are identified by a unique log sequence number, which in Kafka we call it an offset. Now, not only is data written or appended in order, it's also read in order. You just give it an offset and you scan ahead from there on. So this log is what provides the ordering semantics that are required for stream processing. Now, that is the logical version of the log, but physically, if you wanted to scale this log out, then you'd shard it into multiple partitions. And if you did that, then that is exactly the backend of Apache Kafka, where logically a log is a topic, physically a topic lives in partitions that are replicated across a whole bunch of brokers. As events come in, they're appended to one of the partition's logs, and we have a policy for maintaining a fixed window of the log. Part of processing, part of sort of scalability is data parallelism, which is how do you distribute data across machines, which is what we just looked at. But the other part is how do you, scale processing? How do you scale processing across machines? And to that effect, Kafka has this primitive called group management, which essentially allows a group of processes, which is your application, to form a group and coordinate some action. And that action changes whether you're a Kafka consumer or Streams library. So a Kafka consumer, the coordinated action is which consumers own which topics, so that in total they consume the entire topic in collection. As a user, you don't have to worry about any of this. All you do is you embed the Kafka consumer library, you tell it which topics to ingest data from. Whether you start one instance of your application or n instances, the way it works underneath the covers is this consumer library does this group management underneath the covers. So it is actually operationally simple to consume large amounts of data, as you can see. The important bit is that this is actually the same thing that's required for stream processing. Now, in this Kafka Streams, your consumer is replaced by this topology. And the group management does the same thing, which is distribute the input partitions across the instances of your application that embed the Streams library. The really important part is that each of the processes involved in your application are actually peers. There is no special master or slave. There is no special job manager or task manager. It is hence operationally simple to deploy, as well as it scales well from development all the way to production. In terms of fault tolerance, the same group management capability is extremely important. It not only allows you to coordinate actions, it also detects failures. So if one of the instances of your consumer applications fail, the whole group rebalances so that it takes, the remaining instances take up the load of the failed instance. And the same thing is actually useful for Kafka Streams. If one of the machines that runs your topology fails, Kafka Streams automatically detects that failure and it restarts your topology on another live instance of your application. So we actually don't have to rebuild any of this. It's just available through the Kafka client protocol. Then comes state management. First of all, why does state management appear in stream processing at all? And the reason is, if you look at some of these common stream processing operations, you'll notice that there are some operations like filter and map, which are essentially a record at a time. You either take a record and you filter it out, or you send it across, or you take a record and you map it out. You don't have to remember anything about a record in some of these operations. Essentially, they're stateless. Then there are some operations like joins and windowed aggregates, where you, in fact, have to remember something about a group of records in order to compute that operation. So for state management, now you have two choices. First one is remote state. It's really easy. You take your state, and you just stick it at some key value store that you know and trust. This works, but there is an inherent performance impedance mismatch, if it matters. Kafka can process data at a very fast rate, at almost hundreds of thousands of messages per second. But a key value store, when used in this manner, can only process maybe thousands of messages per second. So then the second option is to push your state within your processor so that it's available locally. Now, since all the data that is required for a stream processor is available locally, it is incredibly fast. But then there are several upsides as well. A, it provides better isolation. One fast processor cannot take down the state used by many other live services, which could happen here. And B, it is flexible. This local state is pluggable. It could be as simple as an in-memory hash map, or it could be an embedded RocksDB store, or it could be your customized read or write optimized data structure. So Kafka Streams provides local state, and it provides local state that is fault tolerant. That is important, since if your processor fails, part of your state disappears. That is not great. So what Kafka Streams does is every write made to a state store is transparently written to a highly durable and highly available Kafka topic. So even if your processor dies and it gets restarted somewhere else, which is also something that it does, it merely reads the state from this highly available topic, and it recreates that state before you process more data. So you might think, if every single write in a state database is written to Kafka, wouldn't it run out of space? And it wouldn't, because of a capability in Kafka called log compaction. Essentially, it is a special garbage collection policy that applies to keyed data, topics that have keys. So the way this works is, imagine or consider that every write made to your external database is available as a message in Kafka, where a message has a key and a value. The key is the primary key of the row, and the value is the entire content of the row. So for a row that gets frequently updated, you have several messages that belong to that key in this Kafka log, like the key A here. And for rows that never get updated, there's just the single message that lives in this Kafka log forever. What log compaction does is, in fact, it scans the log periodically, and it deletes older values to maintain only the latest value for a key, which is what you want in your database, which is the latest value of a key. What that means is that every row that exists in your external database also exists in this log compacted topic. So if you want to recreate your state database, you set your offset to 0 and scan this log compacted topic. This log abstraction, when combined with the log compaction capability, actually solves a really hard problem for stream processing, which is reprocessing data. Now, the reason you do want this is, let's consider the example of an application that reads a stream of user visits to your website, and it computes aggregates per geo-region, and it updates some kind of Google Analytics-style dashboard that your user then reads. But then assume that you have to upgrade our application to completely remove some kind of geocodes. Now, when you deploy that application, you know that your dashboard shows incorrect counts for some past windows, which is not a great experience. So what you want to do is, in fact, reprocess past windows to reflect the counts, to reflect your latest business logic. So note that with log compaction, every row that exists in your external state also exists in this log compactor topic. So if you wanted to reprocess something, you set the offset to 0, and you scan ahead and you recompute your state. So here's how this works. You have your application that is reading from the tail, and it's updating the state where your user reads are happening. If you wanted to reprocess the data, you start a separate independent instance of this state, and you set your offset to 0. This is actually possible in a pub subsystem like Kafka because you can independently consume the same topic. Initially, this state starts off empty, but then as it reads, it catches up, it fills up slowly until when it reaches the end. When it reaches the end, now you have two versions of your state store. Your application is, in fact, reading from the old one, but you can flip the switch on your load balancer and have your reads happen from this new version of your application, which now updates the counts, or now it shows the counts that reflect your latest business logic. And last but not the least, time, the concept of time, as I mentioned, is very important to correctness in stream processing. In fact, we've paid a ton of attention to modeling time correctly in Kafka streams. And our work is influenced by this insight shared by the data flow team at Google, which essentially says that stream data is never complete and can and will always arrive out of order. What that means is your stream processing library needs to have a first-class ability to deal with out-of-order data. It shouldn't be an afterthought. So with respect to time, there are two concepts worth paying attention to. One is event time, which is when your event occurs or gets created. And the second is processing time, which is when it gets processed. Now, due to various delays and bottlenecks, these two things can actually converge and diverge. And the loss of correctness in a lot of stream processing systems actually occurs because they conflate these two concepts, which leads to incorrect results. So as an example, let's take the example of windowing. Back to our example of the application that reads user visits, updates a dashboard. So likely it is doing some kind of windowed aggregates. Let's assume that a mobile user visits the website, and right before the event reaches the application servers, it loses network coverage, only to regain it maybe 12 hours later. So 12 hours later, when the event reaches the application servers, now you have two choices. You can either count it in the current 10-minute window, or you can count it in the 10-minute window 12 hours ago, which is when that event actually happened. If you did the latter, then it reflects the true state of the world, which is that you're counting by event time. But if you did the former, then you're counting by processing time, which in fact reflects incorrect counts. The event did not happen right now, it happened 12 hours later. The implication that this insight has is that your stream processing thing has to have the ability to update past data for a stream or update past windows. And this is closely tied to a fundamental abstraction that Kafka Streams provides, which is what I'm going to talk about next. But before that, we've rounded up talking about the fundamental problems in stream processing as well as reactive streams and how Kafka and Kafka Streams manages these. Next up, I'm going to talk about important abstraction that I just mentioned is fundamental to solving, updating past problems or past data for your stream, which is essentially the stream table duality. Now, traditional databases are all about maintaining tables full of state. But what they don't do such a good job of is reacting to streams of events, where an event could be anything from a ping from a mobile device or a weblog. Stream processing systems like Storm are coming from the other end of the equation. They are great at processing streams of events, but computing state off of that stream is somewhat of an afterthought. I will argue that fundamentally what needs to happen in an asynchronous application is combining tables which represent the current state of the world with streams that represents how that state is changing. Let's take an example to understand this duality. This is a very simple example of a Kafka stream. It has 3 messages. Every message in Kafka has a key and a value. The key is, in fact, optional, but exists here. If you notice closely, this stream is special. It updates the value. Later messages update value for keys that are present in the previous messages. So let's call this an update stream. As a thought exercise, let's try converting this update stream to a table. So with the first message, you create the first row, where the key is the primary key of the row. If you read the second message, you add a second row. And the third message, in fact, just updates the first row. OK, that's great. But let's take a step further and take a look at the changelog stream for this table. For those of you who are not aware, databases do this, but changelogs are streams where a message corresponds to any row that got updated. So notice the changelog stream actually is exactly the update stream that we initially started with. So update streams can be converted to tables, can be converted to streams. Streams and tables are dual. So you might think, so what? So let's go back to our retail example, and let's explore this duality in both directions, starting from converting streams to tables. Recollect that streams in our example are streams of sales and shipments. Let's say if we join these 2 streams of sales and shipments, then you get a really important view, which is a real-time view of the inventory on hand table. So here's how this works. You have sales and shipment streams. For simplicity, they have the same format. A key is the item ID and the store code, which is a composite key, and the count is the value. Now note that both these streams are actually update streams. Later messages give updates for keys that were appeared earlier in the message. So we could convert, and these streams are represented internally as tables. Now, as part of the join operation, what happens here is pretty simple. With a message on the shipment stream, you increment the value in the row in the table. And for a message on the sales stream, you decrement the value for that item in the store. So at the end of this, we've converted these 2 important streams into a table, which is the real-time view of the inventory on hand. Now let's explore this duality from the other direction, which is tables to streams. So we have this table, which is the inventory on hand as a result of the join operation. As I mentioned, every table is backed by a Kafka topic. The concept of this is a changelog stream. So this is what a changelog stream looks like for this specific inventory on hand table. The things in orange on the left are the rows that got updated. And every message here is a message where a row got updated. OK, so this changelog stream actually implements, or it enables, 2 very important functions of retail companies that are possibly not implemented this way, which is price adjustments, which is what Amazon does a great job of in real time, and inventory adjustments. So what the reorder sort of inventory application does is it consumes, or it subscribes to this changelog stream. And for every message, it checks the latest inventory count. If it drops below a threshold, it triggers the reorder inventory action. The price adjustment application does something completely different. It subscribes to the same changelog stream, but it consumes messages. It computes some kind of a demand model, which is possibly internal state stored within the processor. And then it triggers the change price events. Now, going one step further, the demand model that is computed by this application, in fact, will have its own changelog stream that might enable some real-time marketing campaign applications. So this is, in fact, useful for several downstream applications, you can see. Now, an emergent property of some of the concepts I just introduced that may not be as obvious is that this stream table duality, when combined with local state that is made queryable, allows us to develop these stateful applications very easily. here's how this works for this example. Back to our example of this join operation where we get an inventory on hand table. If you look at the application view of things, we have several instances of your application that does this join operation. Every instance of your application has a subset of the sales and shipment stream. As a result of that, it has a subset or a shards of the inventory on hand table, which is embedded internally. Now let's consider that Kafka Streams, in fact, makes this internal table queryable. And this is, in fact, a planned feature in Kafka Streams coming up soon, which is queryable state. If you had this internal state table, which is queryable, then your application can now expose a REST API, which allows you to get the latest count for every item in every store. So what we've done here with respect to this application is recollect, this is an asynchronous stateful application. What we've done is we've combined the table, which represents the current state of the world, which represents the current state of the inventory for this retail business, and we've combined it with streams that represent how that state is changing. Now, this may not be practical in all sorts of applications. Oftentimes, you just want to stick your state in an external database and get done with it. However, if you have some kind of lightweight operation, you probably don't want to maintain a distributed database, or if you have a ton of data that you need to process your data, then you possibly will benefit from using local state. That is either a hash table or a RocksDB store, and can be very powerful. Now, some of the things, to conclude, sort of, Kafka Streams helps you build these loosely coupled, stateful applications with ease. In other words, it allows you to build reactive and stateful applications with ease. A common theme that you will observe, and that is worth mentioning here in Kafka as well as Kafka Streams, is that simplicity is valued. What our experience has been is that for successful adoption of infrastructure, operational simplicity is key. For example, this is the architecture that you end up with if, for example, your stream processing system does not have any support for aggregates. So it has to store the aggregates in some external key value store, and hence, deploy and maintain and understand that key value store, keep it in sync with your stream processing job. If your stream processing system has no ability to allow reprocessing of data, then you have to reprocess that data anyway through a batch pipeline that might go through Hadoop. This might work. In fact, this is a popular Lambda architecture. But in the end, what your application now looks like is it's pretty complex. It has to query these two independent views. One is offline, one is online. Merge the results before showing that to the user. This works, but the number of distributed thingies that you have now committed to write a simple stream processing application has increased a lot. This is a lot of moving parts. And that is what might stop application developers from writing stream processing systems with ease. In fact, with Kafka Streams, we've paid a ton of attention to this. We've taken aggregates. We've provided that as optional local state that is available out of the box. We've taken reprocessing and provided that as a primitive that is available from Kafka and Kafka Streams. So now what your application looks like is fairly simple, and that is important in order to make stream processing approachable to mainstream application development. So you might have concluded, you love Kafka Streams, but as you've observed, it only works on top of Kafka. So how do you get your data in and out of Kafka in order to use Kafka Streams? And the answer is Kafka Connect. In the 2009 release of Apache Kafka, the community released a feature called Kafka Connect, which is essentially a framework that makes it easy to develop and use connections to Kafka, connectors to Kafka, to all sorts of other systems and sources. What it does is it solves a lot of common problems that every connector needs to worry about, which is scale out, partitioning, offset management, exactly ones or at least one semantics and so on. And in the 5 or 6 months that we've released this, the community has written more than 30 connectors to all sorts of systems, from Cassandra, Elasticsearch, to Oracle and MySQL databases, and the list will keep on growing. So this is how this all plays out in the big picture. This is what I am interested in exploring, which is the ability to deploy this Kafka-based stream data platform as essentially a central nervous system of the company. It is the basis for development and communication between asynchronous microservices and applications. It is a building block for stateful stream processing applications, as well as an enabler for other stream processing frameworks and clusters. And last but not least, it is the central source of truth pipeline that feeds your Hadoop and your warehouse. This is what some of us made possible at LinkedIn, as well as at several other companies that have adopted Kafka at scale. If you were interested in trying out Kafka streams, you can download the Confluent platform or check out the 0.10 release of Apache Kafka. Admittedly, some of the things I've talked about are ahead of what Kafka Streams has in today's version of the software. But we are looking for feedback. These are early days. Give it a try. If you're already a Kafka user, this is a great way to try out new functionality. A lot of the ideas, that we've talked about here, and in fact, some of the talks at Berlin Buzzwords have adopted, are actually written on the Confluent blog. So if you're interested, check it out. And last but not the least, you can also check out the book that is coming up on Kafka, which is Kafka, the Definitive Guide. Thank you very much.
Thank you, Neha, for this interesting talk. I'm sure there are questions. We have 2 microphones up here. So if you would just want to step forward and ask questions to Neha. We have one.
Hi. I have a question about partitioning in Kafka.
Yeah.
So normally if you want to scale out processing of a topic, you partition the topic and you define consumer group. And as I understand, Kafka will automatically detect failures inside this consumer group and reallocate consumers to cover all the partitions. How would Kafka react to situations where consumers are unbalanced? So some of them there's 2 consumers, one is 2 times faster than the other. So each of them will consume half of the data. But you can easily imagine a situation where the fast one have nothing to do and the slow one will get stuck forever, and the queue will grow infinitely. How does this situation is solved?
Yeah, so there are 2 parts to your question. One is how does in general Kafka consumers deal with falling behind? Do you run out of queue space? And that answer is tied to how Kafka handles back pressure. So it is a persistent queue. You don't run out of memory. It just sits in this Kafka log. What you will see is your consumer's offset starts falling behind, and that is because Kafka's consumer model is pull-based, not push-based. So it actually pulls data as it requires. If it's slow, it's the only thing that gets affected. The second question you had is, how does the load balancing actually work on the consumer? So the way it works is the policy is pluggable. So the default policy that might ship with a Kafka consumer might be something as simple as round robin, or it could be, the one that Kafka Streams uses is co-partitioning. If you want to use joins, where the 2 partitions from the same topic need to end up in the same processor. So in fact, it's pluggable. You could use various different mechanisms. From my experience, what I've noted is that the simplest one is you over-partition your topic, and you have the ability to just round robin the partitions amongst consumers. If there happen to be if you happen to be one particular partition that is hot, then you do end up with a case where you either have to repartition your data so that it scales well, or you just deploy more instances of your application.
But
Does that answer your question?
If the problem is not in the partitioning, but in a consumer, is one of the consumers is slow. So is there a way to partition the data according to consumer performance?
Yes, that's that's what I meant by, sort of custom policies that might be applicable here. Okay. Yeah, so some custom policies are, you might want to, partition or load balance data in your consumer based on resource consumption, where, some of your consumers might be on, sort of more powerful nodes while some may not. And from my experience, I haven't really seen, sort of load balancing policies that work that way, but it's certainly possible. If you write your own, you can plug it in your Kafka consumer and see the effect of that.
Thank you. Any more questions? Well, it seems that you have explained everything very well.
Or I will hang out right after this talk in case any of you have more questions.
Thank you very much. So there is now a... Okay.